So, welcome. If you're here, this is the week 2 for electrical training, and this is our first split week, and so that means we're going to get into more electrical specific stuff. And so basically last week for week 1, which was a shared week, we talked about what microcontrollers are, some C++ basics, and prototyping, and this went into like how to use a breadboard, how to use an Arduino, and things like that. And so now for our first week that's just electrical training, we're going to cover a lot of different things. So first is introduction to PCBs. So by now you've probably seen at least images of some of your team's printed circuit boards. And so we're going to briefly explain sort of how they work and really why we use them. And then in general, we're just going to cover a few basic topics about Eagle, which is the CAD software we use to design these PCBs. And with that, we're going to talk about the concept of what parts and libraries are in the software, configuring your setup, and making an actual part. So I'm sure you've heard the phrase PCBs or printed circuit boards by now, so you might be wondering what exactly they are. So basically, we use PCBs because we want to make more complex circuit designs. So the designs we did in week 1 with the breadboard were like pretty simple, but like if you wanted to add more things to it, like it would slowly just get a lot more confusing. You have so many more components, so many more wires, and so a PCB is able to take a lot of those similar components like sensors, microcontrollers, and other components and condense it down into like this like circuit board type thing where it's a little bit more permanent and it's not just for like prototyping purposes. So on the side you can see 2 pictures. So that's through-hole components and surface mount components. So the through-hole components you're probably the most familiar with because we use them in week 1. So like resistors, you can see the resistors here that are through-hole, and they have the holes within the PCB. And then for surface mount, you can see that they're just mounted on actual pads on the PCB, and this allows us to get a smaller, usually a smaller board than with the through-hole things. So another thing about PCBs is they're usually going to be a lot smaller than like your breadboarded components, and because you can take advantage of surface mount components, you get a lot more complex electrical components out of that. So how they actually work is that PCB is basically constructed with multiple layers. So the first one we can say very top, the silk screen. So that's going to be text labels, graphics. So you might have seen like a RoboBuzz or like your team name on a PCB, and that's what we would say the silk screen is. The solder mask is on the top, which is the thing that repels solder. So if you've seen like the classic green PCB, that's actually, the green is the solder mask. So basically when you're trying to solder onto your PCB, the solder isn't going to attach to that material. So copper is the conductive material. This is actually what's making those electrical connections between components. So in a way you can think about them as like the wires that you have on your breadboard. And then substrate is just FR4 usually, and it's just there for a structure for the PCB. So features of a PCB, so some of these were sort of already mentioned, but you can see here we have an SMD component, so you can see these like the orangish color are actually pads that you can solder to, and then here we have a through-hole component where there's actually like holes in the board which you're going to solder to. And then the white stuff here is the silk screen, so that's like text and labels. And then here are the traces, which are made with copper, and that's connecting different components on this board together. So again, all of our autonomous teams are making PCBs. And so here are just a couple of examples of across the 4 teams. So in the top left here, this is from RoboNav. This is the logic board, which is on Jesse currently. And basically just connecting a board that connects to the computer and a variety of sensors. And here below we also have, for robo wrestling, we have the Gucci control board. And here up top we have Kicker for RoboCup, which helps dealing with actually kicking the ball across the field and scoring. And then here is one for robo racing, which is PoE, or Power over Ethernet, so a communication board, which allows them to have like a network of different boards on their robot rigatoni. So really, the point of this is that we construct a lot of PCBs in RoboJackets, and you guys are also going to be making them. And basically, they're just used to tackle such a wide variety of problems. So now we're going to transition more into what Eagle is and why we're using it. So basically, it's just a computer software to design PCBs. And there are basically 3 stages of development for this. First, you have library and parts. And so these are where components are made and stored, so you can add them to your design. Then you have schematics, and that's where you're making the circuit and electrical connections between components. And then you have the board layout, where you're making those physical connections between the components, which we call traces, so actually routing copper between 2 components so they're actually electrically connected. So down below here you can see a screenshot of what a library looks like, so you have different parts within it. Up top here you can see a schematic, so it looks sort of like some common circuits you might see, and then down below here is the board layout, where you can see different components having been routed together. So the first thing you're going to see when you open up Eagle is the control panel. And so this is just a screenshot of mine. So you can basically access some of your recent files. And on the side here, most importantly, you're able to see some different libraries that you have. So for example, RoboJackets -aesthetics.lbr is a library that I currently have. And so to talk more about libraries, so they essentially store various components that are going to be used in your project, so in your schematic and your board layout. And basically, the libraries in Eagle, they call the main parts devices, and a device is comprised of a footprint and a symbol, which I'll get to in a second. So a symbol is what you're going to see on your schematic. You're going to use this and other symbols to make those circuit connections that you see. So this is, I believe, a symbol of a microcontroller. So you can see VCC, where you can connect it to power, and we're going to connect it to ground here. And you can see other type of digital signals on the side here. And so you're able to draw what we call nets between these pins to other symbols. And then next we have the footprint of the device, and that's basically just the physical representation of your part. So you're going to see that this is basically just a 2D view of what your part actually looks like. So you can see these pads correspond to where the actual pins of this microcontroller are going to sit on the printed circuit board. And so with this, you're going to have this on your board layout, and you're going to be actually creating physical connections between pads to other pads of different components and stuff like that. And so there's a large number of footprints out there, but there's also very large standardized ones. So some of them are here on this graphic. But once you start looking at parts more, you realize that a lot of them have the same sort of dimensions and where of pads and where they're located on a part. And this is because there's a lot of standardization within footprints. So basically, many different parts can have like the same footprint. So a like 10K resistor is probably also going to have like can have a very similar footprint to like say a 1K resistor. So next is the device, and that's what's linking that symbol and the footprint together. And so it does this by, when you do make the device, you have to essentially connect the symbol's pins to what is actually on the, which is actually the pad on the footprint. And so basically this is just mapping it. So you can see that like in the symbol, if you say if you have like a VCC pin, you're actually, and in the footprint, you actually have a pad that is for like power. Then in the device, you're actually going to connect and say, oh, these couple of pads on this part are actually for power. And it's definitely going to make a lot more sense when you actually do it yourselves today. And so going back to the whole like common packages thing, a symbol can have multiple footprints, and you'll see this a lot more as you start looking at more parts. So yeah. So going back to sort of what an example library looks like. So here you can see that we have a device, and you can see here that once you like click on a device in a library in Eagle, it's going to shade in gray what footprint and what symbol it's using. So you can be able to like click on the symbol or footprint and edit it if you need to. And if I went down this list and clicked on other ones, I would see the corresponding footprint and symbol. And so to like help sort of what I said earlier and make it a little bit less confusing, we talked about how a device or like a component can have multiple footprints. So you can see here that this fuse has the normal symbol, which is here, and then has different footprints. And so at least for this fuse, basically this means the 0603, 1206, this means like the pad sizes here are changing just in size. And this is very common, like similar things that you're going to be seeing with like resistors and capacitors as well. And so yes, in general, like a component is just going to have, a lot of components will have just like various different footprints, and sometimes you want one over the other. So that was a pretty short presentation, but that's mainly because the lab for today is a little bit long. And so I'm just going to quickly give a brief overview of what the lab is really about today. And so really it's just setting up your Eagle and making a part. So earlier, again, I mentioned this before, but we should have Eagle installed in GitHub Desktop or Git in Terminal. If you haven't, we'll do that after the presentation. And yeah, the steps for this are detailed in the lab document and in the email, and we can definitely help you if you're having problems with installing either of those. And also we're going to be adding repositories. So we have a repository called Eagle Libraries where we have a lot of these libraries that have multiple parts in it that you guys can use in your designs. And so we're going to be adding that, and that's definitely going to help you as you do like your newer project where you're trying to design a board. And then really the goal of this lab is to step through the process of making a part, because I realized I said a lot of like maybe high level things, but really the easiest way for you guys to like maybe understand the process and like the terminology is actually using the software, right? And making a part. So we're going to start by looking at a data sheet, and we're going to start with making the symbol, which is usually our first step. And so we're going to look at the pin configuration on data sheet, and then with that be able to create pins on a symbol and just create an outline so it looks nice and pretty. And following the process, we're then going to make a footprint. So basically with that process, we're going to be reading the package outline, which essentially gives us the dimensions of the part, just basically telling us like how big the pads are, what are the distances between them. And then you'll be able to place like these pads and then properly size them and locate them on a grid. And this is the process for creating the footprint. And then next, and the last part of the step is creating the device. So again, that's connecting that symbols pins to their physical representation on the footprint. And then we can add some descriptive information for the part, and that just helps us identify it later, and especially helps us when ordering it. If we know like things like the part that's like manufacturing number and stuff like that. So with that, if there are any questions, in terms of making the part, it's very much like outlined in the lab guide.